I will now welcome our first presenter, which is Romeo Saldivar Lucio from Mexico, who will be telling us about climate signals, nature, and implications in resilience building. Welcome. Yes.
Thanks very much. So should I change myself? Okay, that's fine. Okay, perfect. Okay. Hello, everyone. I feel so happy that there's more than 2 people in the session. Thank you very much. And I know because it has been a long week, so I am Romeo Saldivar. Now I have a research position at CICESE in Mexico, in the Northwest. So I want to start reminding that the study of the climate has been partially supported by the analysis of spatiotemporal patterns, just like the PDO, the MEI, the SOI, the NAO, the AMO, many climate indices, which represent only a fragment of the climate system. The thing here is that when we analyze them, they share a lot of different signals, which oscillate in different temporal scales, like around the 50, 60, around 30, a bidecadal signal, maybe a decadal, and maybe so many others. And the interesting thing is that we not find these kind of signals only in the climate indices. We find them in many physical and biological variables, and there are a lot of examples. One of them is the air temperature, the sea surface temperature, global mean sea level, or droughts, or even fish productivity. So in 2019, there's a nice paper by Wei, and where they analyzed the interannual, interdecadal, and multidecadal variability. And they conclude that these signals domain together the rate of global warming. So it seems like these signals are like everywhere, and they are like very important to understand the different changing patterns. So the interannual, interdecadal, and multidecadal signals can be found in the original variables because a numerical property that we know as autocorrelation, which represents the memory of the climate system. And this kind of behavior is of interest because it can be useful for the projections. However, working with autocorrelation sometimes is a little bit tricky because it is the property that represents an important nature of the climate signals, but at the same time, it affects the different methods for detecting these signals. So we have to be very careful about how we use or how autocorrelation affects the different methods. However, this is very useful. I found several applications. One of them, for example, is to project climate changes in some variables like sea surface temperature, even at the regional level, and so we can test like climate change scenarios in the context of natural variability. So before any model fit or projection, we have to consider like 2 main problems of the autocorrelation. The first one is the effect on time series analysis, which often leads to fuzzy or results or bias in the detected signals. So that's important for the projection. For example, in Fourier analysis, we have the problem of spectral regions. instead of very particular signals or periodicities. In the case of wavelets, it seems that some specific signals get lost in particular periods of time. It seems like they are not important anymore, but they are still present. So it depends a lot on what are like the dominant pattern at that particular time. And also it affects the detection when we use a coupled model with cyclic descent and periodic regression, because this is looking for the best fit using the harmonic components, and so it includes and includes and includes more. So again, it doesn't give you like a narrow selection of signals. The second problem with the autocorrelation present in nature is that the signals, in nature, the signals are in a combined way. So it is necessary to identify them, extract them, and combine them again in order to really analyze their effect in the real world. So, for example, when we have climate signals represented in anomalies, and if we apply a cumulative zoom, we are increasing the autocorrelation. We are in some way increasing the detectability of the memory of the climate system. And so if we have a dominant pattern in that particular scale of time, we can see that pattern reproduced only by the increase of autocorrelation. However, we have to be very careful because if we get a set of random numbers and we represent it in anomaly form, and we apply a cumulative zoom, then we will have something like looks like a pattern, like a trend or a period or something like that. But it doesn't mean anything, doesn't represent anything. So, well, it also happens. So this is very important because we have to fight to try to represent better the climate dynamics in space and time, but also to understand the consequences, because this has a direct relationship with the building processes of climate resilience. And the underlying mechanisms in this relationship are these basic concepts. Maybe there are more, but these are the ones that I have explored, which is the psychological distance. This one has two components, one emotional, another one is cognitive. So it is not the same for the people who live the impacts of a hurricane, for example, or a bad fishing season, or something like that, for somebody who doesn't depend on that or never live it. But it also affects the collective memory, the social engagements, which is like some kind of predisposition of the people and the communities to participate or to take action for mitigation or adaptation actions. And it also affects the risk perception. So if we are aware of these basic concepts and we use them in our favor, then we can like activate a positive response for climate action. And all of these statistical approaches to understand the climate signals and these concepts underlying the psychosocial factors affecting the perception of the humans are in coherence with coastal resilience building processes. So it can reinforce the efforts for downscaling, it means like trying to find locally relevant representations of climate and to combine or find different approaches with in situ monitoring and citizen science. But also another way is to approach with the stakeholders, like for example, using drones or photography to represent the local dynamics or ecosystem level changes, which include livelihoods. So having in mind the nature and implications of climate signals and the perceptions in human beings, we have been testing in several variables. As I mentioned before, we built this approach to project and test scenarios in the context of the natural variability for different regional seas in Mexico. And we found like a better yield of this approach in comparison with global models. And also we built a forecast of sardine fishery catches in the California Current for the different ports where it is landed. And it was also very useful to describe the macro scale patterns of the upwelling and downwelling in all this region in the northwest coast of America. And also to describe the behavior of the lobster landings in the different regions of Canada. So, as concluding remarks, I can say that most processes producing low frequency signatures in climate certainly will continue in the future because the mechanisms associated to them are independent of the greenhouse gases accumulation implied in global warming. And the signature of global warming necessarily will happen in combination with the low frequency fluctuations of climate. Therefore, it is relevant to keep deepening our understanding about natural variability, including regional and local monitoring, and the study of interactions with global warming at multiple spatial and temporal scales. So, enhancing the representations of regional and local dynamics will have a positive impact in building coastal resilience. So thank you very much to the sponsors and organizers and to my colleagues, Dr. Armando Trasviña and all the team in Mexico. And thank you for your attention.
Thank you so much, Romeo. That was a very interesting talk. I'm sure modelers in this room have a lot of questions and comments. We have 3 minutes for that, so you are welcome for questions and comments. Any question?
First question, just to know if I'm doing a nice question. You work only with time series, never with also spatial 2D fields, right?
Not yet, but many ideas.
Okay, because my question was, when you did this kind of kernel convolutional correlation, if you ever thought about working with model decomposition or a POD, for example, to see if you could find important modes, just like when you do the shedding of a cylinder or something like this.
Well, yes, I have tried many different techniques, not that in particular. However, I think that there's a very close relationship between what we see in the time series and how then it propagates spatially. So yes, I think that we really want to go on that way and to start like testing now like a better approach. Thank you.
what do you mean by saying that the climate signals are not changed by by warming?
What I mean is that they will continue because the mechanisms are independent, and the global warming signal is going to happen mixed with all this natural variability. That's what I mean.
So, but they will be affected by warming.
In the result, yes, but not the original mechanism.
Yeah. Yeah, we will have discussion later.
Okay, the last question.
Yeah, if I understood it correctly, you are implying that the trend will not affect the natural modes of oscillation. Is that correct?
Yeah.
Okay.
Yeah.
Yeah, because maybe the trend will change the natural modes of oscillation. That's one thing that can happen. Yeah.
We will discuss later.
Okay, thank you so much, Romeo. And now we are moving on to another talk from West Africa. So we will be hearing from Emmanuel Brempong, and he will be telling us about the extreme coastal water levels in West Africa, examining the interplay of tides, wave run-up, atmospheric drivers, and climate models. Welcome.
So good afternoon to us all. My name is Emmanuel Brempong, and this work is part of a bigger project, and this is just one piece of the project, looking at vulnerability of extreme coastal water levels in West African region. And these are the people I collaborated with just to look at some trends in extreme coastal water levels in the West African region. So in general, when it comes to the West African region, as we are all aware, it's a low-lying area. And just like every coastal community, there is an increase in population growth, as we all know. However, one of the major problems, as we all know, is climate change is playing a key role in the shaping of the beaches in the West African region. And so a study by Molalo 2016 has clearly indicated that in the future, still we are going to have an increase in coastal urban expansion. Also, as I have said, population growth is still going to increase, economic activities are still going to increase, and climate change, particularly sea level rise, is going to still increase. And this has become very important because when it comes to the Volta Delta in Ghana, particularly in the West African region, we have come to realize that it's one of the most vulnerable areas in the West African region. And we've also realized that based on this, we need to effectively manage and mitigate climate risks in the area. And so the motivation of the School Wakava project is to first and foremost look at extreme coastal water levels in the region and then link this to any of the climate indices. And this is mainly because coastal erosion and flood has increased over the time in the area. And a study by Dada et al. Has shown that majority of the areas are vulnerable to coastal erosion and then coastal flooding. So when it comes to the West African region, maybe you are not aware of that place because most of us have been talking about different aspects of the world. So I'm bringing you to the south, as our South African friend spoke about the south geographically. It extends from Mauritania to Nigeria all the way to Cameroon. And we have different features there. We have estuaries, we have deltas, we have lagoons, nutrient-rich waters. And I think one of our pilot sites for the coast predict is also somewhere in the Volta Delta, somewhere here. And then wave activities are generally influenced by the Atlantic swells. And when it comes to the tidal patterns, it's ranging between 0.5 to about 1.6. And as I've indicated, it is vulnerable to coastal flooding activities. And so basically, to look at the extreme coastal water level, we use a very simple approach. We looked at the different parameters that will contribute to extreme coastal water level. And we are saying that the factors that contribute to extreme coastal water level are the sea level anomaly, wave run-up, storm surge data sets, and tidal data sets. And these are all from model data sets, not our data, in-situ data sets. These are online databases because in our region, it's very difficult to have in-situ data sets on these parameters. And then we do a simple calculation to say that when it comes to extreme coastal water level, all these factors play a role. So a sum of these, as stated in Raphael et al. 2023, would increase the amount of water level along the coast. And so for our first result was to just first and foremost look at, are these parameters in the extreme coastal water levels increasing over time? Does it really show that they play a role when it comes to the water levels? And what we realized was that over the years from the 1994 to 2015, we see an increase in both wave run-up, both sea level anomaly, both atmospheric conditions. And these are the reasons why we have an increase in extreme coastal water levels in our region. Also, moving forward, what we realize is that we try to spatially look at what these extreme coastal levels represent, particularly in the West African region. And we try to categorize these into different categories. Some are the high resilience based on the extreme coastal water levels. And we realize that Mauritania and Senegal find themselves in that based on the extreme coastal water level that we have obtained. And particularly when it comes to high variability, we have one that is Ghana and Guinea-Bissau. We find them in this area. Now, when we look at the different components of extreme coastal water level, as I have indicated, the sea level anomaly, the tide, the wave run-up, and then also the atmospheric conditions, we try to see which one dominates when it comes to our region. And so from Mauritania all the way to Cameroon, we realize that both wave run-up and then tide play a dominant role in the region. And these are the major factors that are the ones that dominate in our region. And based on that, we also try to classify which areas are more affected or more affected by the extreme coastal level based on the dominance of tide and based on the dominance of wave run-up. On the other hand, as we have identified that wave and tide are the ones that dominate the extreme coastal water level, we try to look at which regions are more influenced by high tide and then high wave activities. And we try to cluster them based on their characteristics when it comes to tide and then both waves. And what we realized that countries such as Guinea-Bissau and then Guinea were found in the high tide regions, whilst Ghana, Liberia, Ivory Coast, and Togo were found somewhere in the high wave regions. Now, to try to look at a little bit of climate change and then look at climate indices, we try to get some data sets in the climate indices variables such as ENSO, such as SAM, such as Atlantic Nino and AO. And these were more or less correlated with the sea level anomaly, extreme coastal water anomaly data sets. And what we try to do is to establish which of these climate indices play a dominant role, or which of these climate indices follows that trend when it comes to the extreme coastal water level along the area. And what we realize is that the Atlantic Nino plays a key role when it comes to the West African region. And this is clearly normal because of our sea surface temperature data sets along the region. And so this is also just a spatial distribution to show us that really the Atlantic Nino shows a high correlation within the West African region. And so basically key insights from this small research shows us that generally when it comes to the West African region, yes, we have increase in water levels and we have increase in flood activities around our region, and this could be attributed to the extreme coastal water levels in the region. We also realize that Atlantic Nino plays a key role when it comes to the increase in the water levels, and therefore when people want to focus more on climate models in the region, they should try to more or less improve the Atlantic Nino conditions with the region, try to get data sets that would be directly correlated with the Atlantic Nino data sets in the region. And so in conclusion, first and foremost, when it comes to extreme coastal water level in our region, one of the things that I did was to just sum up the various data sets. However, that is not the final step. I mean, there are more refined ways to do that. But in the midst of situations where we have very limited data sets, this is like a stepping stone to see what the conditions are in our region before we go into high-level modeling and other things. We also try to use the cluster analysis just to categorize these influence of extreme coastal water level within the region. And this is just to give an information of, in case there are some strategies to curb flooding in the region, maybe where there are some places that have issues with increase in tide or increase in wave activities, and they want to put in a sea defense, they would consider more of wave activities rather than tide or any other parameter based on our cluster analysis. And so basically this study was just to establish the fact that we have issues with increase in flooding within the region, and this could be linked with extreme coastal water level, and this can be a stepping stone to other studies within the region. Thank you for your attention.
Thank you, Emmanuel. We have 2 extra minutes for questions, so please, you are welcome.
Thanks, Emmanuel. Really interesting work. When you have the correlation with the extreme water levels and you found the strong correlation with Atlantic Nino, is that driven by the waves or the surge? Did you then go and look at the individual components to see what it is that's driving those interannual variability?
No, I haven't looked at this internal variability yet, but we just made an assumption that, Atlantic Nino is linked to the sea surface temperature. So we have just made an assumption that the increase in temperature would probably increase the water level in a way, but it would be nice to look at the various components to see which of them really plays the anomaly role in the extreme coastal water level with Atlantic Nino. Yeah.
Thanks a lot for the nice presentation, very interesting. I understand that the data that you based the work on is ERA interim, right?
Yes.
So maybe if you could use maybe more updated data like ERA 5, you could have maybe more resolution and have a bit more refined results. This is a suggestion that I may.
Okay, so this looked at from 94 to 2015. So from 2015 onwards, which we are yet to do, we would consider that one as.
Well, also the resolution should be a bit higher, and also the reliability should be better. So,
okay.
So you could also substitute the interim also earlier with some other more refined data set.
Okay, thank you.
Thank you.
Yes, last question.
The mic was already
okay. Okay, we'll have one more.
Yes, the mic was already here. Thank you, Emmanuel. I think this is a very interesting presentation, and I think the point that is raising around maybe modern data, we need then to take it on board. But I think the other interesting issue that is coming for the cost predict is this idea of maybe us collating the data sets that we have in terms of open source, all that kind of stuff. If there's a project already, then that's fair and good. If there isn't a project, I think Nadia is here. We need then, we are talking about open source. So I'm an advocate of open source. Okay. So we need a portal where you know, if you're dealing with this type of analysis, here is the data, here is the latest data, so here are the links, maybe how you can also retrieve that. So it's a homework. I'm a lecturer, so I give homework.
Yes.
It's a homework that I'm giving to the group. Okay. Then I think the other issue, it's like, that's why I wanted you to come to South Africa, and I think we've spoken about this. We have got a unique situation because we've got the Atlantic and we've got the Indian Ocean. So some of the issues that he was raising there to say what could have been the observations that we're making there in terms of the changes, it would be very good to compare the Atlantic versus the Indian Ocean. And lastly, this is a common challenge when we're talking about climate change scholarship. We need to avoid using mitigation interchangeably with intervention. Okay. When I'm dealing with climate change, mitigation means completely a different thing. I know most of my postdocs and my PhD, I correct this thing regularly. Mitigation in climate change is greenhouse gas emissions and their reduction. So let us be very careful in terms of the language we use in climate change in terms of mitigation, especially the word mitigation is abused and misused. Thank you very much.
Thank you.
Question here and one more online, and that will be it.
Thank you. I just seeing at your climate oscillations, is your Atlantic El Nino does it somehow relate to an NAO as well, or are they completely independent?
They were directly from NAO.
Okay, Ariba. Oh.
Downloaded from NOAA, or what's the question? I know, I didn't take note of it.
So there's a question online there, if you can see. Yeah. The Red Sea and North Indian Ocean are dynamic marine regions worldwide due to their geostrategic location, as they are critical areas and require continuous marine monitoring. How can we benefit from a remote sensing system for marine monitoring to detect variables, pollutants, marine environmental impacts?
I think this question is not for my slides.
Yeah, I don't think so too. It's okay. Thank you.
Thank you. Okay, I have one more question online. So I'm back here. Thank you.
Yes, thank you, Emmanuel. Congratulations for the presentation. Yeah, my question is about the accuracy of data you use. This, I assume that is reanalysis data. So have you tried to do a kind of a comparison or validation of this data with observation data that you collect in Cape Coast, to check maybe this data is accurate? And also, have you tried to see, about the data? Are you sure that you have in every course data in every resolution that you have? How do you deal with that? What do you do? You try to do some interpolation.
Thank you again, Emmanuel.
Thank you.
And now we have another talk from Loretta Conachia from Delta Race, who will be telling us about using self-organization to build climate resilience ecosystems. Welcome.
Thank you very much. As my title says, I will be using concepts of theoretical ecology, like self-organization, and explaining to you how we could apply them to improve ecosystem restoration, and particularly the case of salt marshes. Well, why do we need to restore ecosystems? Well, one of the reasons is that there's been, in the last few hundred years, very big losses of coastal wetlands. Some estimates say up to 50%. And if I can say, in the case of the Netherlands, this percentage is probably much higher, up to 80%. But we have seen before in the talks how important wetlands are. They can be used as nature-based solutions, and they can adapt to sea level rise because they can accumulate sediment and in that way grow with the sea level. So it is really important that we try to restore them. So also to compensate for all the wetlands that have been lost, there are new approaches to build wetlands. One of them is called managed realignment. As you see here, if you have a dike protecting the coast, you would open or breach the dike and let the tidal water again in. But I am asking you, do you think it is just so easy to create an ecosystem from scratch? Well, it turns out it might not be so easy because ecosystems also make their own patterns. And this is what I talk about when I mention self-organization. So these patterns just evolve through the local interactions between the organisms and their environment. So in the case that I show here with mussel beds, arid vegetation and coral reefs, there are all these feedbacks between plants growing and water flow and sedimentation. And in the particular case of salt marshes, you can see there's also a lot of patterns. You can find this whole vegetated area that is dissected by this network of tidal creeks with main channels, side channels, and side-side channels, and so on. But if we look at how the restoration of marshes has been going so far, well, we can see this has not been very successful in most of the cases. I show you here an example of a natural salt marsh, and in the blue part you can see the area that has been restored. But you probably notice some big differences. So the natural marshes have lots of creeks, lots of meanders, and highly branched. But if you look at the restored areas, there's still very few channels, and they only seem to follow what used to be the agricultural drainage ditches. And well, there are also other examples where after many years, decades, there's still no vegetation yet, which is the point, like why we are trying to create a salt marsh. So in order to, well, investigate if these restoration projects have been successful or not in developing resilient marshes, we took a look at 14 different restoration projects in Netherlands, Belgium, and UK. And we also looked at two different types of restoration approaches. One that you see here, the creeks are excavated, so they're just man-made at the start. And that's made also in the hope of speeding up the development of the salt marsh. While in the center you see the case where just the dike is open or breached, and then all these channels evolve by themselves. But probably you can already visualize some differences. So here the creeks are just apparently equally wide everywhere, while in nature the creeks tend to become thinner and narrower, because as you go inland there is less water that needs to pass through them. So already, well, I'm pointing to some of the differences. But we then also compare to natural marshes, because that's our, the reference that we're trying the restoration to move towards. So in our comparison, we looked at the structure of the patterns, so in particular the geometry of the channels, so how long, wide, or deep they are. Also how well they would drain the water. And finally, with a model, we looked at how resilient they were to sea level rise. So how well could the sediment be transported in the channels and trapped by the vegetation. And in that way, the marsh could then grow with the sea level and become more resilient. So the first part about looking at the different patterns was done through remote sensing. So we looked at digital elevation models that allow us to get all the elevation of the area. And with Python, we extracted the channels and looked at different properties like cross-section areas or depth and width, and also analyzed them over time. What came out from this comparison is that, as we can see by eye, restored marshes are different. They have a significantly lower extent of the channel network. They are also flatter. As you can see, there is overall less landscape heterogeneity than in natural sites. And they're also less efficient in draining the water, because by having less creeks, it also means that the water needs to travel much more to find the channel and to then be drained out. And well, another aspect that we found in our analysis is that these restored creeks are usually not in balance with the hydrodynamics. If you look at the size of the marsh, so the amount of water that needs to drain out of a salt marsh, there are generally some relations between the size of the marsh and the size that the channel should have. And if you look at the blue points, all the natural marshes tend to fall along this line. But if we put the restored sites on top, you can see that some are just way too big for the area, like this one, or some are just way too small. And keep in mind that this is also on log scale, so these differences are really quite big. So what we can conclude is that the designs of creek in restored marshes is also not optimal because it deviates a lot from what is the natural pattern. Well, to look into resilience of salt marshes, we, of course, could not limit ourselves to just remote sensing data. We also looked at how we could use modeling approaches to see how marshes evolve over time. And we have this model that is able to, can be used to simulate the evolution of a salt marsh, as I said, just based on self-organization concepts and these feedbacks between the plants, the water, and the sediment. Over time, this leads to the development of this vegetated marsh dissected by channels. And if we compare this to some Google Earth images of real salt marshes, we see that we can capture these multi-scale channel patterns with main channels that branch much like a tree into side branches, side branches, and so on. So once we had this model, we, however, had to expand it because we were interested in resilience. So how well can these channels bring the sediment into marsh to compensate for sea level rise? So we added another component, which is the sediment transport. I will show you now a short video of the simulation. So you can see there is an open site that would bring in the sediment, and we can now use the model to compare if we have different types of channel networks, how well are these channels transporting the sediment. So to test resilience, we took each of the 14 sites, the 14 restoration sites that I mentioned before, and we recreated them in the model. But in this case, we did two different sets of simulations. So in one case, we start the model with the creeks as they have been made in reality, which is the one you see here. And on the other side, you see what the area would look like if we just follow self-organization principles. So we start with just a flat landscape, and we let our model predict how the area should look like. Probably you can already see some large differences. First of all, the one on the right seems to reach higher elevations overall. So this already is suggesting that the self-organized case is more resilient in terms of sea level rise. But what you can also see is that the shape of the channel is completely different. So here, the creeks are just taking the shortest path to the open, to the open part of the landscape. And that's, of course, because water just takes the shortest path that it can take. Well, in this case, we have some quite unnatural turns and shape of the creeks. So this is already pointing to some differences. And we did this not only in cases where the creeks were excavated at the start, but also in the case where no creeks were made. So we just recreated all these sites into the model. Well, what came out of this analysis is that, indeed, if built marshes are really deviating from the natural patterns of the creeks, as in this case, then their sedimentation is much lower than if the creeks would have followed self-organization principles. So the closer you are to a natural pattern of creeks, the more resilient your system will be. And in fact, if we then look at sites that didn't have creeks imposed at the start, then we don't really see a difference between what our model predicts in terms of sedimentation and what would happen if we recreate the creeks as they are in reality. So this is to say that if the deviation from the natural pattern is higher, then resilience would also go down. And to conclude, I would like to say that we didn't use this approach just to look at past restoration projects, but we also tried to use it to advise future restorations. So this is an example of a tidal marsh in the Netherlands. We collaborated a lot with the managers of the area. They showed us their plan for the site. And you can see well, here a bit better. They had a whole idea to have like a single channel that would go from one side to the other of the area. When we put that into our model, you can see that after a number of years, what would happen is that this channel would fill up here and here. So it would end up looking quite different from what they had in mind. And we also tested what this area would look like if you just didn't make any channels. And it turned out that there would have been, there would be a better idea. So I was happy to see that in the end they considered also our analysis for their plans, and they eventually settled for a quick design that is much more similar to what would come out of our model. This brings me then to the main takeaways of my talk. What I've shown you is that man-made salt marshes are different. They're different in terms of structural patterns and in their ecosystem functioning, but they also appear to be less resilient. So what I would suggest for climate resilience is as much as possible to mimic the self-organized natural creek patterns to be able then to have more climate resilient marshes. And with that, I thank you for the attention.
Thank you, Loretta. And now we have 3 or 4 questions.
Thanks, Loretta. In Australia, we have huge problems with acid sulfate soils when human modification of salt marshes changes the salinity dynamics. Have you looked at trying to model the salinity as well as sedimentation to see the impacts, the changes between natural and modified salt marshes in terms of salinity?
Yes, not myself, but a PhD student in my former group. She looked at salt intrusion. Yeah, because that is also a problem in the Netherlands, and particularly for what I showed you before is a freshwater marsh. So in this area, there is a big risk and problem with salt intrusion. So what she's used is pretty much a similar approach to model the sediment moving, but then in this case for the salt.
Arriving farther?
Well, if they have constructed like very regular ditches, then the salt would stay longer inside because of the same problem that the water doesn't drain so efficiently. If the pattern is more natural, then the salt would be flushed out quicker.
So I actually have a tangential question to both that and that. Yeah. So in my country, we're experiencing a transition where we are realizing that some saltwater marsh is now colonizing a freshwater marsh area. And the assumption, because it's really just an assumption, we haven't done any kind of monitoring to prove it, the assumption is that it's because of saltwater intrusion. And so what I want to know is not necessarily have you considered that, but alluding to some of the material that you mentioned just now in terms of the demonstration of self-organization for climate resilience, I feel like it might have a bit of an implication for sea level rise and climate resilience as well for experiences like what we're having with the colonization towards freshwater, towards saltwater marshes. So I wanted to know if that's anything that you've considered, or are you interested in doing any kind of research related to that? It's more of a personal question as well, I guess.
Yeah, that would be really cool. I didn't so far as much, but yeah, we should talk about that. And I'm happy to hear your first-hand experience. Okay.
For the very interesting presentation. I find very interesting this consideration about the geometry of the channels. I wonder how dynamic is this geometry, if it can change in time, like if there are extreme events, how can they affect the shape of this channel, and also if in time these artificial channels can evolve to resemble more the natural ones, and in how much time?
Yeah, usually
it's a big question.
Yeah, it is. From what we looked at, like for natural marshes, I would say within 30 years, it is pretty much stabilized. And once the channels are formed, they are quite stable. But for artificial ones, it's a bit of the opposite problem, because if the size is not correct for the area at the beginning, then they either tend to fill up, or you have like a lot of channel at the entrances, but then nothing else develops in the rest of the area. So yeah, that is a bit more complex, and it depends a lot on the case.
Very interesting talk. These kind of dendritic formations are very common in kind of estuarine riverine areas. But it's in your model, do you take the different behavior or the different component of the different marshes that you have, like the question that was being asked here, if like they behave differently, do you have it? Or they just let it grow as it is, or how does that site house the natural?
Well, yeah, we decided because having 14 sites would have been quite a lot. Yeah, very difficult also to make recreate each site with the conditions as they were, and then it would also not allow us, I think, to make this comparison between like self-organized conditions or real-world conditions. So we assume that the conditions are the same in terms of like the tidal range, and we consider mostly the shape of the area. So yeah, that is.
So it hasn't got like the different kind of marsh response into it or anything. It's just like
No,
the
no.
way the natural behavior of channels.
Yeah, it is more like idealized condition in that sense.
Last question.
Thank you very much for a nice presentation. I stepped out for a moment, so forgive me if this question you already had set up. But the sediment composition, how much does that, and delivery source for the simulation, how much does that impact kind of the results that you're getting? So I guess my question's coming from I often hear about sediment-starved marshes, you know, on the east coast of the U.S. and sort of having the changes in land use kind of impacting the source of delivery, but that marshes can also get sources of sediment locally. And I didn't know if you had kind of explored that within
we did in part of the paper we played around with the inundation rates and with the sediment input rates to then get an idea of like which condition would make the salt marsh more or less resilient. So to find what would be then the threshold between the two, because you could have like a lot of sediment and then that can compensate for a very high rate of sea level rise.
Oh, Loretta?
Thank you.
Yeah. And now we will hear from Charlotte Lyndon from the University of Liverpool, who will be telling us about the sensitivity of estuaries to climate hazards.
Good afternoon, everyone. I'm Charlotte Liddon. I'm a lecturer in coastal dynamics at the University of Liverpool. And today I'm going to talk to you about the sensitivity of estuaries to climate hazards. So this was a piece of work conducted as part of the UK Climate Resilience Programme. So coastal and estuarine flooding occurs when an extreme river or sea level exceeds a certain threshold. And globally, it's one of the most dangerous and costly natural hazards. In terms of impacts on people, it's caused over 3 million deaths since the 1700s and over $1 trillion in economic losses. Specifically in the UK, 1 in 6 properties, or nearly 3 million, are at risk of flooding, and there are annual damages caused of over £540 million per year. It's the second highest risk to civil emergency in the UK after pandemic influenza. So flooding can have substantial impacts on human health, food security, And here we're specifically interested in a certain type of flooding, which is compound flooding. So compound flooding occurs when two or more extreme events, or sort of medium-sized events, they don't have to be extreme in themselves, can have substantial or significant impacts because they occur in close succession or at the same time. So what we see on screen here is a video on the top showing precipitation, which is occurring at exactly the same time as a change in atmospheric pressure. So we have a drop in atmospheric pressure at the bottom, which through the inverse barometer effect can raise our sea level with a storm surge. Happening at the same time as we see this big extreme band of precipitation coming across, which subsequently increases river discharge and volumes of water within our estuary. And we can track the progression of a compound event through our estuary by tracking or observing the river discharge as shown by our hydrograph in blue. So a hydrograph is a way to describe a river flood event. We can then also see how our hydrograph rises steeply and occurs nearly at the same time as our peak in sea level, shown here by our black line. And what can really be useful to help us to define a compound flood event is what's represented by this purple line at the top, and that's our lag time. And that's the difference in time between our two extreme events. And a shorter lag time indicates those peak events occur closer together and would maybe create a more compounded event. Previous research that we had conducted looking at the occurrence of these compound events in every estuary in the United Kingdom showed a prevalence for compound events occurring on the west coast of the UK, largely because of the steeper, more mountainous catchments that we see there, so river discharges move through the estuaries quicker. But also that the duration, or the average duration of a hydrograph caused by a flood or a more extreme rainfall event occurs or has a duration of less than 24 hours. So we need sub-daily river discharge records to be able to track these extreme events, to be able to accurately capture lag times and compound events. So in recent years in the UK, we've seen a quicker succession of winter storms progressing over the country, so more extreme events occurring over a shorter period of time, causing substantial amounts of flooding. This is the Dyfi estuary in West Wales. So we'd previously shown that the Dyfi estuary is vulnerable to these compound flood events. We've got evidence here of a time when we had a high river discharge occurring nearly at the same time as a high sea level, causing a substantial amount of flooding. And so what we know from the literature is that we're likely to see into the future an increase in the magnitude and frequency of events likely to raise our river discharges and sea level. So compound flooding in the Dyfi could be getting worse into the future. And we wanted to find out if that was true. How is climate change going to impact compound flooding in the future? Will it become more of a problem? And should we account for this change in our hazard management strategies? So we used downscaled marine and fluvial projections, which were both derived from the same global climate model shown at the top. This is the Met Office HADGEM 3 60-kilometre global climate model. It has 12 ensembles and is run for the RCP scenario 8.5. On the left-hand side of the screen, our global climate model is downscaled to NEMO AMM7 in 12 ensembles again. Transient runs from 1980 to 2098, providing us with hourly sea levels. On the right-hand side, the global climate projections are downscaled to a convection permitting model, which enables us to better represent those extreme and intense storms that are going to cause those peaks in our hydrograph. The CPM is then used to drive a hydrological model, which for the first time provides projections of hourly river discharge. So that hourly river discharge allows us to be able to represent the hydrographs that are likely to cause compound flooding. At the time of this study, the only place in the UK where we saw these hourly river discharges produced was in the Dyfi in West Wales. So that forms the case study for the rest of this talk. So because our projections of marine and hydrology are both forced from the same global climate models, using the same 12 ensembles, we can compare dependence between them. We can pick out the extreme compound events, analyze them, and then feed that into an impact model to understand how flooding may change under those conditions. So we first of all handle each of our projections separately to get a better grasp of what the surge climate is likely to do in the future. We detrend the storm surge record and take out sea level, so we're just exploring the meteorological component. And what we see here is actually storm surge magnitude is not likely to change, or when we look at the percentiles, not likely to change much into the future. But we calculate return periods, and we use a bootstrapping technique on the annual maxima to project or expand our record to allow us to produce a return period up to a 1 in 50-year event. If you take a look at the green vertical line, which represents a 1 in 20-year event, a 1 in 20-year event is likely to increase by 4% from 0.7 meters in baseline conditions. So we split the record up into 20-year time slices to be able to describe conditions in the baseline. And then we see in the far future, a 1 in 20 event likely to increase to 0.73 meters. We can take it from the other perspective as well. So if we follow the horizontal purple line, we can see that a 3/4 of a meter surge is likely to become more frequent. So changing from a 1 in 28-year event in the present day or baseline conditions to 1 in 23 in the far future. We do similar analysis on our river discharges. So we have our percentiles for our 3 baseline time slices on the left. Our outliers are shown by the red dots, and they mask our kind of more interesting trend. So we zoom in on the percentiles at the bottom, and we can see that our 75th percentile is increasing slightly here. So potentially an increase in our more extreme events, but a decline in our median and a sort of continuation of our mean, giving an indication of the variability of the climate and how the changes in precipitation are likely to impact extremes. We see more variability here, more change in the return periods than on the storm surge alone. So if we take that green line again and look at our 1 in 20-year discharge event, we see that by the far future, the magnitude of a 1 in 20-year event, in the Dyfi at least, is projected to increase by nearly a third, so up to 795 cumecs. If we again have a look at our horizontal purple line, which it represents 600 cumecs, this is expected to become much more likely. So it goes from being a 1 in 17-year baseline event to a 1 in 4-year event by the end of the century. So next, we take both of these time series or projection conditions together, and through a peaks over threshold analysis, start to better understand how extremes in both conditions are occurring. So we have our hydrograph in blue. We pick out all the peaks on the river discharge that exceed a 3-month moving mean plus the 95th percentile. And we identify all the peaks in surge that occur within an average duration of a hydrograph. For the Dyfi, that's 20 hours. And with those co-occurrence or those codependent peaks, those pairs of surge and river discharge, we first calculate a correlation coefficient between their magnitude, shown here on the left. So we handle each ensemble separately. Each ensemble represents a different set of parameterizations in the global climate model So because we handle each ensemble separately, we show a spread of what the results are across the 12. So we see dependence in some ensembles of quite a low dependence, but others ensembles show a higher dependence. But overall, what this is showing is an increasing dependence between extreme river discharges and surge. In the middle, we see the number of times both drivers are extreme in those projections, and that's increasing into the future. And then on the right-hand side, we see that time lag, that duration between our extremes is potentially decreasing or shown to be decreasing here as well, which will have implications for maybe the volumes of water we see in the estuaries. We take these conditions and we feed them into an inundation model. We use list flood, and we have in grey here a baseline 1 in 50-year event. Then in the kind of yellowy colour, we have a 1 in 20-year event under sea level rise for the far future. And then even more flooding is caused by a 1 in 50-year event into the future. So our flood footprints are increasing into the future under these increased magnitude compound flood events. So this work represents a novel use of physically consistent, hourly resolution, hydrological and marine projections to assess future compound flooding. Fluvial drivers of flooding are projected to exhibit greater changes than magnitude in marine drivers. We're likely to see an increased dependence and reduced time lag. So overall, we need to be considering joint probability in flood hazard assessments in our estuaries. I know I'm running over, but I'm just going to show one last update. We only did this for one estuary in the west coast of Wales, but the Environment Agency are paying us to roll this out for every estuary in England now. So what we're doing in the INVEST project, working with DEFRA and the Environment Agency, is a national scale characterisation, not just of changing dependence in estuaries in the UK, but now also changing water quality, and we're quantifying how residence times will change in estuaries around England. As part of this project, for the first time, we've built the highest resolution bathymetry DEMs in the UK. These are a 10-metre resolution and will be available to people in the future. And we've updated our data framework by using marine projections from 75 estuaries, and this is computationally very expensive, so we're starting off with creating future flood projections for 10 catchments in England, but that will be, hopefully by the end of their project, people who are producing those projections, that will be 600 projections. Thank you very much for your time.
Got questions?
You will soon discover that I never raise questions. What is interesting in your presentation is this challenge we have about the return period, which the engineers gave us. Engineers. Right. You see, we were told about don't build in a 50-meter flood zone, 100-meter flood zone before climate change. We are still talking about don't build in the 100-meter flood zone, 50-meter flood zone. Why were they talking about that? This was like in 100 years or whatever years they were giving us then, this event will return. And I can assure you, not in Durban, year in, year out, we are seeing serious floods. So the question then that goes as we go as cost predict into the future, there are some knowledge systems that are becoming redundant. So this is not for you, but this is for the group. So this idea of a return period to me really does not make sense. So what we need climate resilient infrastructure, whether it's 1 year, 100 years, 20 years, whatever return period. So I think there's something that we really need to disrupt in terms of where we are going. Like I'm saying, these engineers went to school before climate change, and they are maintaining their way of doing things, which actually is obsolete. it's obsolete. The blueprints are obsolete. So these are some of the things that we need to look at. So it's something that we need to then consider moving forward. So I like also the idea of maybe you're looking forward and mapping that you are doing in the compound events. In the ICC, UNFCCC, I sit in the non-economic loss experts group. There is now movement from using extreme events. There's movement towards using slow onset events, then rapid and sudden events. Because a slow onset sea level rise can also be extreme. Ocean acidification can also be extreme. So then we are trying now to differentiate by saying we have got slow onset events and we've got rapid and sudden events.
I think it's a nice comment about the return periods. It's a really challenging metric to use. I suppose it's a metric that some of us are familiar with using, but maybe there are better ways of showing it. Maybe there are different or better ways of visualizing the results. And I think the challenge can also be how are return periods used to communicate actually uncertainty, the likelihood of an event happening, and maps can be a really nice way to show maybe a range of different scenarios. And that's where actually maybe using that approach of taking a return period and using the results that we find for a future magnitude event in a series of what-if scenarios and sensitivity testing the amount of flooding you see under different conditions. Because a 1 in 20-year event, it's not necessarily just one value of river discharge and sea level we're likely to see. It's a huge range. And maybe using different visualization tools can help to better communicate that uncertainty as well. But yeah, I think it's a great comment.
So thank you very much about interesting, very nice presentation, clear. So in addition to completely agreeing with Godwell about the improper usage for building infrastructure of only one parameter, which is this return period, instead of looking at the complexity of the issues, which we might have as an outcome of cost predict, having many cases that will show the non-efficacy of having this kind of way to plan an infrastructure. I think the other part that would be nice is to have your study done in the opposite case of lower precipitation future climate. Because you're going to be dominated by more precipitation in England, while in the Mediterranean, for example, we are dominated by low precipitation on land. Maybe not on the water, but anyway, on land. So it would be nice to run the opposite scenario in an area like the Mediterranean, where the compounding is different.
Yeah, it's a great idea. That's something we're starting to do as part of this wider assessment for water quality, is looking at, in the UK, so slightly different climatic conditions, but low flow river discharge, high sea level, and likewise, so sort of different coincident conditions that will then have implication for changing water quality. But then applying that regionally somewhere different is interesting in itself. So yeah, we're starting to do it, but for the UK. So maybe we'll do it somewhere else.
Well, I liked a lot the comment about the terminology of return period. I agree, it is very misleading. The reality is that it is a proxy of probability, so we should call it in this way. It is the probability that an event happened this year, which is different from the one that the same event will happen in 50 years with the climate change. So this could be maybe a way that is less misleading to describe this concept. And the second question that I wanted to ask is, you didn't consider the sea level rise in the storm surge, I guess?
Not in the actual storm surge, not in this bit, no.
Yeah.
We took out the sea level rise because we only wanted to see how the storm surge itself was changing.
Yeah.
But then in these flood scenarios, we added sea level rise back in as well. So yeah, for example, this orange outline is our 1 in 50-year event with what the the UK climate projection sea level rise is at the end of the century in this location.
At the same time, the sea level rise increases the probability that an event of a certain size will happen in terms of impact.
Nice comment. So actually that maybe doesn't
and so probably you should, it would be interesting to show it in terms of a return period or rather
so maybe
probability.
that 1 in 50 by the end of the century is actually a 1 in 10. Yeah.
It's just a bit of history that we sometimes forget, but that analysis has been done by Philip Woodworth, and he has shown that just with the sea level rise, your 1 in 1,000 years become 1 in 100 years in all that map that you are showing. So I think it's really important that you take it into account because it's have quite an effect.
Just a quick comment on the period, because I think it's worked on our side, because everyone knows that if it's reducing, you strengthen the severity. So the return period, it's a good reference that we have to use, because they know that if the return period is reducing, so it's getting more and more dangerous. So I think that it's working on our side.
Okay, thank you,
everyone.
Charlotte. Yes. Yeah, okay, now we are going to hear the insights from Mankuga and Focus. I've wanted to hear this since the events started, so this is nice. And so Philip will tell us about the nature-based and technological solutions for coastal resilience from these two projects.
Okay, thank you very much. So I'll try to summarize what we have been doing so far. Most will be on the Makonga project, which I'm on and which we are testing in Ghana. So I'm from the University of Ghana, and I think this slide speaks for itself. Coastal erosion and flooding are on the increase. I think my predecessor Ima has talked much about it, and then for us to be able to tackle the issue, data is very important, and also scientific knowledge through our analysis and modeling is very critical for that. And as he mentioned, if it comes to our region, data is a huge problem. We don't have a lot of monitoring going on there. And so we are lacking in terms of that. But also when it comes to where we have all the data available, also there's a need to improve what is delivered to the users. Finally, there's a need to improve it to make it more user-friendly for them. And just to give you an overview of the situation and along the eastern coast of Ghana, which happens to be one of the sites that was predicted is working with. You see, erosion, coastal erosion is a major issue. And this site was part of my PhD. And this was the situation when I was finishing my PhD. You see, most of the community has been lost. But as we talk right now, there's no single house left there. The whole community has been wiped away completely. And you can see other areas also suffering the same thing. And in this video, you see an incident of a surge happening, wave overtopping, entering the community and destroying, displacing people and destroying properties. So that's the kind of overview of what is happening along the eastern coast of Ghana. And of course, there are interventions, and as we talk, most of the interventions are in this gray spectrum. A lot of groins being constructed, revetments, and you can see them springing up all across the coast. And now, most researchers are pushing that we should start shifting towards the green aspect. And because, of course, there are a lot of challenges if you just keep in this spectrum in terms of cost, in terms of the impact on the downdrift side. What we see, especially with these groins in our region, is that you see downdrift, you see erosion increasing massively. And then people are crying out, okay, then we'll go and put another groin. So it just keep going. And so now there is a cry for let's start to move towards this region and see how we work with nature. And that is where Makonga comes in as one of the first projects looking at how we can start looking at nature-based solutions to help solve our problem. And this particular project focused on the use of mangroves. And one of the key objectives is to be able to develop a digital twin methodology so that we can then have room to explore all these alternatives of bringing a nature-based solution to see which one works for our region, which one we can use to help our region. And so as a baseline to start, we started putting some data together. As already mentioned, data is a big issue, but luckily for us, just recently, through another project, they have done some nearshore bathymetry mapping. Up to this time, all we have is the global data, GEPCO, but they have some nearshore bathymetry that has been collected recently. And then they have initiated some profile monitoring for that area since 2023. So that gave us a good start for this modeling. And as you can see, this is basically the area. I'm sure Ima has shown the general area. So this is Ghana, and that is the eastern coast. And this is where one of the hotspots along the entire coast of Ghana. So we pick one of those areas, and then using the little data that we have, combining with global wave and data, we set up a one-dimensional model first, using the profile, using XBeach. And so for this, we just look at, okay, let's see whether we are able to capture the erosion that is happening first. And then we try two simple scenarios. If mangroves are at the back of the beach, what will happen? In some cases, yes, you see on the ground there are mangroves. Where the situation is favorable, they kind of are on the shoreline, basically. Then also try if we put them in the intertidal zone, which on the ground doesn't happen actually, but we are just exploring to see what works. And so we tried these two scenarios in the one-dimensional model to see what results we are getting. And so basically with the trying to capture the erosion. So this was the profile for June 2023, which was measured on the field. And the red one is the profile for July. So you can see within the short period, there was massive erosion, about almost 11 meters within that short period. And so the first attempt was try to predict the July profile. And after a number of calibration, we got close. The berm erosion was almost accurately captured. Also in terms of sediment erosion, slightly overestimated by 3%, probably due to wave run-up. Not much of the sediment is able to be pushed to the back, so it's available to be easily carried away. But overall, we had an RSME less than 1 meter, which at least gave us some confidence to move to the next stage of just introducing the mangroves and see how the shoreline responds. And so here are some of the initial results. So when we put mangroves at the berm area, just at the back, that may not be the exact precise location, just for illustration. You see that at medium density of mangroves in that area, you see that we have erosion reduced up to about 64%, and the sediment erosion reduced up to also about 48%. When we put more mangroves, I think it doesn't really help the situation anyhow. So at least with the medium, we have some good results there. And then if we introduce mangroves in the intertidal zone again, which I said doesn't happen, The results are really promising, of course, expected because there's a lot of damping happening there. So the shoreline is almost always preserved without any form of erosion. But again, that is not really, unless we are able to do some form of engineering to make that happen. That doesn't exist in nature. So, but at least it's promising where mangroves are existing, at least erosion is slowed down quite significantly. So those are some of the initial results we are getting from the Makonga project. And what we are doing currently is we want to look at the alongshore, because this has just been one day looking at the profile changes. How does the alongshore dynamics play in? So we have set up the 2D, which is almost advancing in terms of calibration. And then it gives us the opportunity to test more options. We are in our neighboring countries, they are trying out to bring in sediment, the sand motor option, combining with vegetation. In our initial discussion with some stakeholders too, they are asking us to try other vegetations aside from the mangrove, because some of them don't think that in some areas the mangrove will work, which is true in that case. So yes, just to show some of the next steps we are doing, yes, the 2D setup calibrated. This is all, somewhere here, about 5 kilometer stretch for a start. And then we have also set up the hydrodynamic model using the schism, which we have also kind of calibrated quite extensively. And the agreement in terms of the water level looks good. So the next stage is looking at how we can put this together in terms of combining the two models, and then advancing our exploration with nature-based solutions using the two-dimensional X-pitch model. So that is so far what we have been able to do with the under the Makonga project in terms of gradually developing the digital twin methodology, which is help to explore all these options and then help us to gradually begin to move away from the completely gray interventions that have been done so far. Yep, so just some 2 slides on the focus project. I think you have heard a lot about it already. Here we have a lot of data to be able to work with. So it's more, the focus is just improving the final products that are given out for use by partner institutions. Maybe I've been warned, so so the focus then is just an operationally fit for use coastal information service for societies along the European coast. Thank you very much. I think we can get more information. If you scan the QR code, you can get more information on what is happening, especially on the focus project. Thank you very much.
Thank you, Philip. We only have 2 questions. Any question?
Hi, thank you very much. I was thinking if you have considered maybe a combination of nature-based solutions like modeling the seagrass in the intertidal and then having the mangroves behind, and how that will work out.
Okay. In terms of our conditions there, I'm not sure. We don't have seagrasses occurring naturally because it's a high energy zone, so they will not survive. So the focus is more on the beach side. So we can maybe vegetated dunes, things like that. We may try that. But in the water, it's not possible because of the high energy of the area, yeah. And it's quite steep, quite a steep beach.
That's my question, because whatever we have in Mexico, it's either behind or at the beach, as you show your mangroves. And so I'm thinking, how do you manage to grow mangroves in the high breaking area, and how does that look, and how successful you are?
No, so like I said, we haven't done that. This is just modeling to see. We just introduce it to see what. Yeah, it's not possible to do that on the ground. Yeah. So we are just trying the model at least calibrating it as much as we can, then we start focus. So most of the focus will be what is behind the beach, not in the intertidal zone. If something in the intertidal zone, then it will be a gray approach, having a breakwater, offshore.
I just wanted to know if you've had any consideration towards, as you said, so far it's really just theoretical, right? But something that could also be theoretical is possible sites. So have you thought about doing a site suitability assessment? I know you've done like along the berm, but I mean in the area that you're looking at as well. Have you done an assessment to make sure that they are the conditions that mangroves require to thrive?
Yes, yes. So actually, where I showed that the community was completely gone, that area was also covered with mangroves. So mangroves naturally grow in that area. Yeah, they naturally grow in that area. And then recently, the community members themselves tried to plant something, but the season was selected was very bad. The seedlings couldn't survive the storm. So that is one issue we are also looking at. Because, yeah. So naturally they grow there, but it's how we are able to keep them to grow to a certain stage to be able to offer the protection that they can.
Okay.
Can I say last one?
Yes.
Thank you, Mangoka. Mangoka, you are the first Coast Predict project, which was financed by AXA. And it was a German Ghana specific project. Okay? So you were financed under Coast Predict. And so great success for this.
Thank you.
And very nice modeling. And so Adem Mao, she told us that people in the past were eating the mangroves. And that's why they are not there anymore.
Oh, yes. They, they rely on it for so many things.
Yeah.
One of the things is that they use the mangroves for smoking fish. They use it for construction. So there's always cutting of mangroves. That is one of the main drivers of it being lost in the area. Because they said that when they use it to smoke fish, it gives it a unique taste. And so they will not replace it with yes, if anything. So it's difficult convincing them to move away from that. But that is one of the things Makoga is engaging on, to convince them to look at other alternatives. Yeah. All right. Thank you.
Okay, now we have our last presenter, Sema Shirinov from CMCC. And he will be presenting about the coastal ocean dynamics, the impact of wave and morphodynamic processes on the northeastern Tyrrhenian Sea. Welcome.
Hello everyone, I'm Seymour. I'm a PhD student at the University of Bologna, and although I stay here at Lecce at the CMCC, and I work with that lot of smart people there, and I will be focusing on northeastern Tyrrhenian Sea, specifically on impact of waves and morphodynamic/sediment transport processes. I'll jump right in with no motivation given, and we work here at the coastal digital twin of the ocean, and it's composed of several components such as waves given by with wave 3 model, then circulation given by SHIFM MPI. We couple those two, and we can also run force one but with another one. I won't be stopping much on this, but there is a preprint available that you can have a look at. Then the digital parts come through vegetation, and I will pass through that quite briefly because it's been already partially presented. And then the morphodynamic/sediment transport, which is embedded in our SHIFM MPI, which is being forced by waves and circulation, and it has indirect impact of vegetation through the waves. although the direct impact should be further considered in the future to account for trapping effects, for example. So vegetation module, most of the studies do use rigid vegetation. We use the same, but we add up flexible vegetation term in terms of effective leaf length that's driven with the bottom orbital velocities. It's not as impressive as yesterday's presentation, which actual flexing vegetation, but yet it does the job. It dissipates the waves, which is embedded into the bottom friction sink term. Then we also have seasonal growth patterns, given the loads of data at the site. And we merge that, given the synergy between the model, numerical model, and the data within the WaveWatch model. So to briefly showcase you the validation of this flexible vegetation model, we conduct our test case at the coast of Mallorca in Spain, using the domain of the study of Infantes. There are loads of measurements given at that event, which had a strong stormy event during 2 days, I believe it was. And we conduct several experiments, one without the vegetation, one with the rigid vegetation that, as expected, shows complete dumping of the waves. The no vegetation experiment shows absence of dumping, and then there is flexible term that approaches our observation given in a black solid line. Yeah, so let's move on. We use that model and we add up the seasonal pattern and we apply that to the coast of Civitavecchia. On the left, you see the domain of the coastline, which shows you 4 sites of community interest. And we see also in the middle the division of that of this domain in terms of the substrates, these seagrass tribes. We are considering Posidonia oceanica, which is quite abundant in Mediterranean Sea. And using those substrates, we define 3 phenotypic traits of our Posidonia oceanica. And there are 15 stations through which the data were collected, and these are the characteristics of those seagrass leaves. And this is the reconstruction of seasonal growth patterns using the data, simply interpolating them across the year. And the data were collected through decade of measurements. And just to know that there are from November through February, there is like slow season, because in October, September, there are high intensive waves arrive at the coast, and the maturity is in around July, August, and September. So we expect higher dumping effect over that period. The results show on an annual wave dissipation map up to 40% of dissipation. Well, I didn't mention in the Infantis test case, they also seen 40% of dumping that we validated through the model. So it's similar effect we see here. We can see the mean values over the year, across the year, over the vegetation canopies. And we highlight that there are 18% reduction of waves over the sites of community interest, and 24% for different phenotypic traits of Posidonia oceanica. Then the seasonal effect takes up to additional variation of, it adds additional variation of up to 10%, which is quite significant to neglect. It's and there is also a link to have a look at the preprint. Now on to the sediment transport. This is motivation. This is how it looks like. The domain is divided into these 2 sections. The water column that is driven mostly with advection and diffusion of suspended sediments. There is a vertical flux that is expressed in terms of deposition and erosion. It's driven by settling velocity, which is not trivial to define. And there is bed load transport, mostly rolling and slipping of the sediment grains, and if there is enough energy input, then they get lifted up and remain in suspension. And there is an active layer that represents our morphodynamic process, and that active layer is divided. The active layer is the top layer, but the underneath layers are divided into several of them, and each one having its own porosity. These are basically the drivers behind that image. Advection and diffusion with the addition of settling velocity. Settling velocity can be given by different definitions. Soulsby, Stokes, can be derived through machine learning techniques. We show the vertical transport is drives the deposition and erosion, and it's a function of equilibrium concentration at the interface between the bed and the water column. The bed load transport can be also given by many formulations, but here we choose this one because it considers waves and currents. Although I must say there is no there are no secondary currents, meaning there is no helical effect considered. But since we discretize in vertical, we do consider the effect is present, and yet that to be studied, but on the river bands. And then these two drive the seafloor evolution, given the Exner's equation. So quickly on the idealized test case, this is the test case of Wu Lonyu. It's tidal inlet with 1 meter of waves forced on the top from the north. These are ROMS and FV models, and well, the color bar is saturated, but we see the pattern. The pattern is the erosion in the middle and deposition on the lateral sides. And then we see our results, which has different form, but it's also erosion in the middle and deposition on the sides. We look at the profile to see and do some sensitivity analysis to showcase how waves affect the morphological change. This is basically the change of the bed thickness, and the radiation RS stands for the radiation, which is given by the red line, and it introduces half of the it accounts for the half of the impact on the bed. And there is a similar study that's been conducted recently. We're now trying to replicate that case. What is just important to see that it has similar shape. That's all I can say for now. We jump onto the cost of Fiumicino. With the real test case of Fiumicino, it's the motivation behind it. There is a construction of a harbor, and so they need some information. We have abundance. The other reasons are that we have abundance of information at the site. There are river discharge information, and then we can extract, for many decades actually, we can extract using power law, quadratic fit, the concentration at the river mouth. Then there is bed morphology information for 5 different classes of sediments, and we can use that to define 5 fractions within our model. These are the outputs. So we run the simulation from August 2020 till May of 2021. We can look at the bed load transport, sediment concentration. We can look at shear stresses at the bed. We can look at some cumulative effects in terms of average grain sizes. And then we can also look at the seafloor evolution. But the question comes, how do we validate this stuff? So we use for that the Sentinel-2 satellite cluster, which has a resolution of 10 meters. We use a case-2 regional coast color atmospheric correlation neural network algorithm to extract total suspended matter. I must note that it also accounts for the cohesive sediments, which we do not model. This particular frame is of when the satellite passed through the region in February of 14th February of 2021 at 10 o'clock. And of course, we have same time step of our model. We see the differences. They are quite different, although we have river discharge and the resuspension works. But the reason behind it, again, as I said, the resolution, which plays a significant role in sediment transport, both the horizontal resolution and the vertical discretization. And the difference is of 5-fold. We have the total suspended matter from satellite, which is 5 times more than our model. So to see why it's doing that, we can look at the transect line along that bigger river mouth. And this is the profile of our suspended sediment concentration. And you see how it settles quite quickly, just 500 meters off the coast. To compare that with the satellite data, and you see this difference, again, 500 meters off the coast, but before that is quite reasonably well fit. And to account, to improve that model, we would do some calibration of sediment concentration at the river mouth. We will also use generalized vertical discretization coordinate system instead of the Z geopotential. And as George Avery showed, that has quite significant impact on salinity. So we believe we will have similar effects. We can use the radar measurements to validate the seafloor evolution. The data is available at the Touche University that Simone Banamano works on. And then we will eventually, once calibrated, study the effect of the mobile seafloor on the dynamical sea level equation. Thank you.
Thank you for a wonderful presentation. We are out of time, so we will only take one question.
Thanks. Thanks for the presentation. I was curious about, from the different models that you use to compone the final model, or maybe there is already in literature, sorry for that, if you did some parametric studies. For example, the model, I saw that the model of settling velocity was quite old. Like, for example, yes, in river places, the shear forces between the two different buoyancies of the river flux and the sea flux creates these finger-like structures that enhance the settling velocity. And I don't know if you, maybe among all the different things that could be checked, thought about, okay, these models, can they help me or not?
There are different formulations for sure. There are laboratory studies that have conducted. Recent ones I've seen of 2014, I believe, of the study of Taisi. And they all kind of fail to properly provide that information. So there are more tendency to move to data-based formulation of that. So we did run different parameterizations. As I said, Stokes equation, we use Soulsby, we use several others, but they do change, especially if we limit the threshold, we provide this threshold for settling velocity, they do improve the model. But yet, if there is no sufficient handling of vertical discretization, if there is no high resolution at place, it won't be resolved just with that.
Thank you all for such a wonderful discussion. We are over time, so I won't say a lot. And now I will give the floor to
Thank you, Helen. Thank you for our 6 speakers. Great future we are looking. Very good discussion. But bear in mind, we are trying to look at gaps. Take that in mind first. But before I let you go, we'll just have spent another 6 minutes or so. 6 more minutes, but we'll delay 10 minutes for more coffee time. For you to talk. Okay, you will come back at 4. Don't go first. Don't go first. Let me invite Loretta to sort of introduce the few posters. A very quick talk only. Thank you.
Is it good? Okay, great. So